hydrogen and a fluorine, as well as a methyl and an ethyl group. Fluorine has the highest atomic number of those directly connected atoms, and so it's priority number 1, and hydrogen has the lowest priority, number 4. But how are we going to decide between the two carbon atoms? When we have two of the same atom, we're going to write out a little list of all the connected atoms for the two that we are comparing between, and we're going to make sure that list is in order from highest atomic number to lowest. For this methyl group carbon atom, the connected atoms are H, H, and H. Hydrogen, hydrogen, hydrogen. And for the ethyl group carbon, we have C, H, and H. One carbon, and the other two things that it's connected to are hydrogens. Then we're going to go down both lists until we find the first point of difference. In this case, it's just the first atom. So carbon ranks higher than hydrogen. Therefore, the ethyl group carbon ranks higher than the methyl group carbon. And so we're going to give ethyl priority 2 and the methyl priority 3, respectively. If you apply the rule from the previous slide and you still don't have a winner, you just repeat the process one bond away. So let me show you an example. In this ring, there's one chirality center. The 4 substituents are hydrogen, a fluorine, and the 2 ring carbon atoms. And because the ring is asymmetrical, those carbons are considered different groups. Hydrogen is going to rank number 4, and fluorine is going to rank number 1, just like the previous examples. The 2 carbon atoms that we're comparing are both connected to a carbon, a hydrogen, and a hydrogen, C, H, and H. So our 2 lists are the same. That means we have to move down one more bond. Now we're comparing these 2 carbons, and this is a situation that we haven't run into before. We have a double bond. When you have a double bond, you consider it as 2 single bonds to the same atom. So for example, this carbon, we would consider it bonded to a carbon, and a hydrogen. And this other carbon, we would consider it to be bonded to a carbon, and then another carbon. So this carbon that's connected to 3 carbons is the winner. And because it came from this side of the ring, we would make this carbon priority 2, and then this one priority 3. Once you have all your substituents ranked from 1 to 4, it's time for the next step. The second step in assigning the R or S configuration is to view the molecule with the 4th priority group, which is usually a hydrogen atom, pointing away from you. Usually this means that you are looking at the molecule so that the hydrogen or the 4th priority group is on a dashed bond. That means it's pointing away from you, the viewer, and into the page. We want to be able to look at our 1, 2, and 3 priority groups as if they make a steering wheel, and the bond between the chirality center carbon and the 4th priority group is like the steering column pointing away from us. So when you're checking out your molecule for its orientation, look for that steering wheel with number 4 in the back. For now, we're going to move on to the next step, and we're only going to use examples where the 4th priority group is on a dashed bond, but later I'm going to give you a ton of strategies to use for cases where you don't have the 4th priority group pointing away from you. With the 4th priority group pointing away from us, we can then draw a circle tracing through groups 1 through 3. On this molecule, I would start at the number 1 and then draw my circle through 2 and 3. And here on the enantiomer, the mirror image of that first molecule, we would also start at 1, and then the circle goes the other way through 2 and 3. Notice how those circles were traced in opposite directions. This is our differentiator. This is the key difference between these 2 enantiomers. If the circle that you traced is clockwise, the configuration is R. And if the circle that you traced is counterclockwise, the configuration is S. An easy way to remember this is that from the top, clockwise goes to the right, so R for right, and for the other configuration, the S, from the top, it goes to the left, and the Latin word for left starts with S. That's why it's S and not L. So that one's a little more complicated, but if you can remember R for right from the top, then you will remember how to assign the configuration. Let's try putting all of these steps together for an example. Here's a molecule. And this molecule has a chirality center at the top. There's a hydrogen, an implicit hydrogen on this carbon, which means that there are 4 different groups attached to that carbon. A methyl, a hydrogen, and then 2 unequal sides of a ring. So first let's rank those groups. We knew that hydrogen will be the lowest, it'll be 4th, and then we have to compare the 3 other carbon atoms in order to rank them. The top carbon on the methyl group is connected to H, H, and H. The carbon on the bottom right is connected to a carbon and then two hydrogens. And the carbon on the bottom left is connected to another carbon by a double bond. So we count that as two carbons and one hydrogen, C, C, and H. So being connected to two carbon atoms gives that bottom left carbon a higher priority. So it's going to be number 1. The bottom right carbon will be number 2, and then the top methyl carbon will be number 3. Chirality center would have the S configuration. Another possibility is using the double swap trick. Because swapping two groups on a chirality center generates the enantiomer, doing a second swap will regenerate the original molecule. And you can use this to your advantage to get the fourth priority group pointing away from you on a dashed bond. In this example, we're going to swap the hydrogen and the fluorine, and also swap the ethyl and the chlorine. So these two are drawn in different perspectives, but they are the same molecule. And now to assign that configuration, chlorine would be number 1, fluorine 2. If you come across a molecule where the from us, and yes it is, the hydrogen is on a dashed bond. So now we're going to begin at priority number 1 and trace a circle through 2 and 3. And we ended up with a counterclockwise circle. So that means the configuration of the chirality center is S. So that example was great because our fourth priority group, our hydrogen, was already pointing away from us on that dashed bond. But on an exam, your professor might not be so nice. You need to know what to do if you come across a molecule where the fourth priority group isn't drawn on the dashed bond. The hydrogen or that fourth priority might be pointing towards you, or it might be in the plane of the page, and you need some strategies to help you solve those problems really quickly and be able to assign R and S no matter which way the molecule is drawn. So here's a few of those strategies. First, and I'd only recommend this if your molecule is very simple, you can imagine rotating your molecule and redrawing it to put the fourth priority group in the back. For example, we could draw an axis right through the chirality center like this, and then we would do a 180-degree rotation. So that would switch the sides of the methyl and ethyl groups, and it would bring the hydrogen to the back and move the OH to the front. Then we could rank the other groups. OH would be 1, ethyl would be 2, and methyl 3. So this chirality center would have the S configuration. Another possibility is using the double swap trick. Because swapping two groups on a chirality center generates the enantiomer, doing a second swap will regenerate the original molecule. And you can use this to your advantage to get the fourth priority group pointing away from you on a dashed bond. In this example, we're going to swap the hydrogen and the fluorine, and also swap the ethyl and the chlorine. So these two are drawn in different perspectives, but they are the same molecule. And now to assign that configuration, chlorine would be number 1, fluorine 2, and ethyl 3. And so this chirality center has the R configuration. This is my favorite method to use when you have a hydrogen or a fourth priority group that is in the plane of the page. That means it's not on a dash or a wedge, it's just on a flat bond in line with the page itself, just like on this molecule below. So here I'm going to imagine what I would see if I was standing within the page, looking straight down the bond from the chirality center to the hydrogen, which is pointing away from me. So if I'm standing there in the page, I would see a chlorine atom down and to my right. I would see a fluorine down and to my left. So chlorine down to my right, fluorine down to my left. And then straight up above my head, I would see that ethyl group. So I'm going to imagine those three groups as if they are my steering wheel. I've got that steering column between the chirality center and the hydrogen pointing away from me. So if I traced that circle from group 1 to group 2 to group 3 in the view that I am standing in, that circle would be clockwise. And so this chirality center would have the R configuration. Finally, when the hydrogen or the fourth priority group is pointing to the front, so on a wedged bond, you can do two things. You can either swap the circle or you can swap the rule. I'm going to teach both and just use the one that you are more comfortable with. If the hydrogen is on the front, so on a wedged bond pointing towards you, and only if this is the case, you can draw the circle from 3 to 2 to 1 instead of 1 to 2 to 3. And then apply the RS label as usual. R for clockwise, S for counterclockwise. I like to do it this way because that keeps the R to the right intact. So in this case, doing the circle from 3 to 2 to 1 would give us the R configuration. We could instead draw our circle as usual from 1 to 2 to 3, and then remember to swap the rule. So then by swapping the rule, we would give S for clockwise and R for counterclockwise. Only when the hydrogen is pointing towards you. Of course, if we do this for this same molecule, we do the swap the rule method, we would also get R. So here's our first practice problem. This is asking us to assign the absolute RS configuration to each chirality center. This molecule has two chirality centers. This one up on top has an implicit hydrogen. We'll just draw it in on the dashed bond, but we're going to look at the other carbon first. So we know that hydrogen is going to be priority 4 because it's the lowest atomic number, and bromine will be number 1. And then comparing between the two carbons, this one's attached to 3 hydrogens, and this one is attached to 3 carbons, 2 from the double bond and 1 from the single bond. So that carbon is priority 2 and the methyl will be priority 3. And now to view our molecule, we're going to put ourselves in the page. So I'm going to draw myself here, and I'm going to draw what I'd see if I am looking down the bond between the chirality center carbon and the fourth priority hydrogen atom, just like this. So I would see to the top, sort of the rest of the molecule will use R, down and to my right a bromine, and down and to my left the methyl group. So I'll add those priorities on so I can draw my circle. And then the circle is going counterclockwise. So this is an S configuration. On the other chirality center, hydrogen will rank 4, nitrogen will rank 1. This carbon is attached to CH and H, and this one to CC and H. CC and H is better than CH and H, so the double bonded carbon will get priority 2. And this one over here will get priority 3. We've already got a hydrogen in the back, so our circle can be drawn. It's counterclockwise, so this is also an S configuration. Okay, here's practice problem number 2. We're going to assign R and S to each chirality center in this molecule. This molecule also has 2 chirality centers, here and here. Both of those chirality centers have an implicit hydrogen, so let's draw those in. On this one, that hydrogen is on a wedge, so it's pointing out towards us, and on the other one on a dash, so that means it's pointing away from us. We'll start with the left-hand carbon here. OH is going to rank 1, and hydrogen is going to be the 4th priority. And then this carbon here is connected to CH and H, and this one is to H, H and H. So the CH and H is better, it's 2, and H and H is 3. Hydrogen's pointing towards us, so I'm going to draw my circle the opposite direction, from 3 to 2 to 1. And so I get clockwise, which is R, because I used the swap the circle method. Instead, I could have used the swap the rule method, so drawn my circle normally, 1, 2, 3, And then a counterclockwise circle is S, but we change it to R for swap the rule. So in both cases, you get R. So the other carbon has fourth priority on hydrogen. This carbon is connected to O, O, and C. This carbon connected to CH and H, and that one connected to Cl, H, and H. So chlorine is the highest atomic number of the first connected atoms, comparing with oxygen and carbon. So that one gets first, that one gets second, and this one gets third. And hydrogen's pointing away already, so we can just make our regular circle 1, 2, 3 counterclockwise. So this one's S. If you've made it all the way to the end, it means you're putting in time and effort for your organic chemistry studying, so good for you. I have a feeling you're going to do well. And if you want to help even more people find this video, I would love it if you could give it a like. And if you like this style of tutorial, feel free to check out my website. I've got lots more resources on there, including more R&S practice problems. See you in the next one. Happy
All right, so this is just a brief video, the first one I had wanted you to watch, which gives you several ways that you can assign the R and then the S configuration. And I think this is being captured on the recorded video, so the more you watch, then you pick out the particular strategy that will work for you, so that you will be able to assign the absolute configuration. There is a second one, but there's a hand up. So let me pick that. And there's a second video also which talks about this R and S. Then I will go to the other stage. So yes, Esiama, your hand is up.
Doc, we thank you. We will be glad if you could share the links to us, because at some point, the video was in and out. We couldn't see clearly the diagram she was showing. So we'll be glad if you could have got the links.
I saw that I lost my what do you call it? My network. My link went off.
Okay.
And so I had to even go back to the video again so that to capture everything again. But the rest, I will still do well to share some of these links with you, which will help.
Okay, sir. Thank you.
Yeah. Why I'm taking my time at this point is that the assignment of the R and S configuration is very key. And so I did introduce you. Now you've watched this. I want us to see if you can watch another short video which also talks about this R and S configuration, because you will be examining on a number of molecules that will be given to you to indicate the R and S, and possibly go ahead to give the IUPAC name of which the configuration R and S will have to be part. So we need to get it well, and then I'll introduce you to another thing later. So let me, just a minute. Please, can you see the video well? If not, let me know. Can you see the video?
Yes, sir. No.
Yes or no?
No.
No. Okay. I've paused it. So let me get the settings down right.
Prelog rule.
Can you see now?
Prelog rule. So this is the rule that we are going to apply to help us.
Okay, so
Two
I'm
things that are
starting.
very important when we're looking at the R&S configuration, and therefore we are going to look the type of bonds which are normally used. One of them is wedge, and one of them is the dash. So normally in R&S configuration, you will find these two types of bonds. So this is our wedge, and this is our dash. So what's the difference between the two? When we have an atom on the wedge, it means that that atom is in front of us. It means that its direction is towards the viewer. So it's coming towards me from the plane or from the page. While when it is dashed like this, it means that it is at the back. That atom is at the back, away from me, the viewer, and meaning that it's going into the plane. In R&S configuration, we have to apply a rule called can. So there's a guy called can Inglot, can Ingol prelog rule. So this is the rule that we are going to apply to help us assign a molecule R&S configuration. So what does this rule say? The rule simply says that the first substituent attached to the central or attached to the chiral center is assigned a priority from number 1 to number 4 from number 1 to number 4. And this is based on the atomic number. So for example, if I have this carbon here and I have 4 substituents attached to it, let's say substituent number 1, R1, R2, R3, R4. So if these are the 4 substituents in a carbon, then I'm going to list them or to give them priority based on their atomic number. The largest the atomic number, the first priority it gets. And remember, these are atoms which are directly attached to this carbon, and this carbon should be a chiral carbon. We have done what is a chiral carbon, and now we know that it's a carbon which is attached to 4 different substituents. So there are rules that there are sub-minor explanations under can Inglot prelog rule. And the first one, we have said that the atoms directly attached to the chiral centers gets first priority. So for example, if I have this is my bromine, so this is our chiral center. All right, this is our hydrogen here. So these carbons here, or these atoms, in this case, you have this carbon, and you have these atoms and this atom here. So these are the atoms which are given first priority. I cannot go to this carbon here before I consider this carbon, because this carbon is not directly attached to the chiral carbon. So these are the carbons that I'll give first priority, including these other atoms. Now, sometimes it happens that now, in this case, for example, let me increase another carbon here. So if you look at this chiral center, these 2 carbons are also attached to another carbon. So it reaches a point in which whereby these 2 carbons are the same. These have 2 protons, these have 2 protons. So what do? We go next to the other carbon which is directly attached to the ones. And then in that case, to help us look which one is going to get the highest priority. So for example, now if I put chlorine here, so if we check, this carbon is directly bonded to carbon, chlorine, and 1 hydrogen and 1 hydrogen. Well, if you look at this carbon here, it is directly bonded to hydrogen and another hydrogen, and it is bonded to another carbon here. So you have carbon, hydrogen, hydrogen. So in this case, this one will take our second priority because bromine is greater than these two carbons. So this one will have our first priority, and then this side will have our second priority, and then this side will have this third priority, and hydrogen is going to have the least priority. Most of the time, hydrogen has the least priority, number 4. Sometimes you find that you can have carbon which is doubly bonded to carbon. It simply means that this carbon is bonded to two different carbons. Even if it is carbon oxygen, it simply means that this is a carbon bonded to oxygen and another oxygen. And if you have a triple bond, it simply means that this carbon here is bonded to 3 different carbons. So those other carbons that we don't see, we call them the ghost carbons or the ghost bonds. So that's some of the things that you need to consider. For example, if this is my stereochiral carbon and this is my bromine, this is hydrogen, and then in this carbon here, too, and then let's put the hydrogen. So this bromine here is going to be our first priority because bromine atomic number is larger than this carbon. And then if you look at this carbon and this carbon, this one is simply bonded to hydrogen and another hydrogen and another hydrogen, while in this carbon, because it is a double bond, so it's bonded to one carbon and another carbon and this hydrogen. So this one is going to take our second priority, and this is going to be third priority, and this is going to be our fourth priority. So that's what it simply means. So now let's apply this now to assign R and S configuration. In normal situation, then when we go clockwise, this we get our R, and when we go anti-clockwise, we get our S configuration. So this is our S configuration in a normal scenario. But so let's look in this example. So let's call this our A. So it means our B we can have still on the same side. So our bromine can now be on the wedge, on the dash, and this one can still be on, OH can on the dash. And then when we look, so this is our B, and when we have C, we can still have them. So we can maintain our bromine here on the wedge, bromine, and then we put this one on the dash, and then our D here we can put it. So this is R, then we can maintain this to be our ash or dash, so bromine, and then because this one, then we can change it into OH. So these are, so we have this molecule. So let's see what are the possible stereoisomers that we can have in this case. How many of them that we can have? So now we need to assign a R and S configuration in this case. Remember, we have said that when we move clockwise, that is our R, and when we move anti-clockwise, that is our S. However, this can differ depending on the arrangement of the atoms. So now, if you look carefully in our A, so this is our carbon number. Let's call 1, 2, 3, 4. In carbon number 4, let's start with carbon number 4. In carbon number 4, our bromine, it is in front. So it means that our hydrogen, it is going to be at the back. So an hydrogen is given priority number 4. So if we look right now, bromine, the atoms which are directly attached to this chiral carbon, so carbon number 4 is the chiral carbon, and therefore our first chiral carbon, and bromine is given the first priority, so this is our number 1. And if then we look at this carbon and this carbon, so if you look here, we have 3 hydrogens. Here we have 3 hydrogens, and this carbon, it is directly attached to this carbon, so we have carbon and 2 hydrogen, and therefore this is going to be our second priority, and this is going to be our third priority. And remember, our bromine, which is our first priority, it is in the front and hydrogen is in the back. So it is very easy. In this case, we can move clockwise and giving carbon number 4 an R configuration. Let's look at carbon number 2. Carbon number 2, still oxygen, OH is in the front, and therefore our hydrogen, which is the least priority, it is in the at the back. So let's look oxygen, carbon, and carbon. Which one is the highest priority? It is oxygen. So this is going to be our priority number 1. And then if we look at this carbon here, it is directly attached to carbon, so it's going to be carbon priority number 2, and this is going to be priority number 3. And because our oxygen, our first priority is in front and hydrogen is at the back, so we can move easily anti-clockwise, and this is going to give us an S configuration. Now let's look at B. So if we look at B, still this is our carbon number 1, 2, 3, 4, and 5. So now, one important thing that you need to know is, look what is given. So in this diagram, bromine, it is at the back, and therefore our hydrogen will be in front. So our hydrogen, which is priority number 4, will be in front. So let's look. This is our carbon number 4. So bromine is number 1. And if you look, carbon number 3, it's as high priority compared to carbon number 5, because this carbon is directly attached to this carbon number 2. So we have carbon, and here we have hydrogen, so carbon, hydrogen, and this is only hydrogen. So this is going to be our number 2, and this is going to be our number 3. So we have number 1, number 2, and number 3. So we need to move this way, all right, in the R configuration. However, hydrogen, which is priority number 4, it is in the front, so it is blocking us to view the molecule directly, and therefore we need to change our direction so that we can view the molecule in the right way, and therefore we are going to move this way, and making this one, instead of R, is going to be S configuration, because carbon number 4, sorry, priority number 4, it should be at the back, but it is in front, so it is blocking us to go in the right direction. Therefore we have to turn. Let's look at carbon number 2. Carbon number 2 is also chiral carbon, and therefore oxygen here is still going to be our first priority, and making this carbon here to be our second priority, and this our third priority. And in that case, we have our hydrogen, which is the fourth priority. It is also in front. So now, if this is number 1, number 2, number 3, so we need to come this way. We need to come this way so that we move in the S direction. So we need to move in the S direction. But when we reach at carbon number 3, hydrogen, which is supposed to be which is the least priority, it is in the front, it is blocking us to view the molecule directly. So we need to change our route, and therefore instead of becoming S, we are going to have our R. So in B now we have our S and R configuration, and in our A we have R and S configuration. Let's look what is happening in C. In C, still 1, 2, 3, 4, 5. So let's start with carbon number 4, because bromine, it is in the wedge, meaning that is in front, and therefore our hydrogen, it is at the back. And if we look at priority, bromine will take the first priority. Of course, now carbon number 3 will take the second priority, and carbon number 5 will take the third priority, and hydrogen will take the fourth priority. And hydrogen, it is at the back, so it's much easier to move this way, and therefore carbon number 4, we are going to have R configuration. But let's look at carbon number 2, which is our chiral center here, chiral carbon. Hydroxyl group, or OH, it is at the back, meaning that our hydrogen is going to be in front, and it is the priority number 4. So this one is priority number 1, this one is priority number 2, and this is priority number 3. So we need to move in number 1, 2, 3. All right, we need to move in the S direction. However, when we reach at carbon number 3, the carbon number 4, priority number 4, which is in the front, it should be at the back. All right, so meaning that we are viewing the molecule in a wrong direction, we need to put it in the right direction, and therefore we are going to change this way so that we can have our R configuration, and therefore here we're going to have R configuration. Let's look at carbon molecule D. So we have 1, 2, 3, 4, and 5. Once again, if you look at our carbon number 4, which is our chiral center, we have bromine at the back, so meaning that we are going to have our hydrogen in front, and therefore actually if you look at D, automatically it will going to be the opposite of C, which is going to be SS. But let's prove it. Let's prove it if D is going to give us SS. So now bromine here is priority number 1, and of course this one will be priority number 2, and this is going to be priority number 3. All right, so in this case we need to move this way so that it gives us R configuration, but you realize that hydrogen, it is in front, and therefore meaning that we are viewing the molecule in the wrong direction, so we need to take the other route. So we need to move in the other direction so that we can view the molecule in the right way, and therefore if we change, it's going to give us S. Let's look at carbon number 2. Carbon number 2, the OH group is in the front, and therefore our hydrogen is going to be at the back, and based on the alignment, OH will take first priority, and this one, carbon number 3, will take the second priority because it is directly attached to this carbon number 4, so that is carbon, and then it is also attached to 2 hydrogens, so that is H, while this one is only attached to 3 Hs. So carbon number 2 will have the second priority, this is third priority, and hydrogen, of course, it is the fourth priority, and therefore we can simply move into S direction, giving us SS. So with this one, with just like I've said, D is the opposite of C, is give us SS. So now how many do we have? We have now, so in C, so let's just write them properly. So C, so this was A, this is C, this is B, this is C. So C we have R, and D we have SS. So let's look at them properly. So we are seeing that the maximum stereoisomers that you can have here are 4. Okay, they are 4. Let's prove. Let's take how in each molecule, either A, B, C, or D, there are two chiral centers, right? There are 2 chiral centers. So if there are 2 chiral centers, remember we said 2N give us the maximum number of stereoisomers, and N represent the number of chiral carbons. In each molecule, you have seen that any molecule we take, their N is equal to 2. So meaning we're going to have 2 to the power N is equal to 4, and therefore the maximum number of stereoisomers that you can get is 4. So let's list them. So that one can mean that you can have RR, and then we can have SS. Let me just put them properly here. So we can have R, and we can have RS, we can have SS, and we can have SR. So if you look RR, that is the configuration that is for C, RS, which is the RS, which is the for A, SS is D, and SR is B. So now if you look this molecule directly, then we can have now what we call enantiomers and diastereomers. So if you look R and R, so we're gonna have A, B, C, and D. So our RR is our C, so this is C. Let me use another ink, so this is C. SS is D, RS is A, and SR is B. SR is B. So now, just like we have said that stereoisomers are molecules with the same molecular formula, but different attachment of the atoms in their 3 dimensions. So with the stereoisomers, we can get, with the stereoisomers, if this is stereoisomers, we can get enantiomers, and we can get diastereoisomers. So now if you look A and B, so we have A, B, C, and D. So if you look molecule A, which is if you look C, R and R, and D, S and S. So I want you to pay more attention. If you look at molecule A and B, molecule A and B, this one, the first one that we had here, you see the chiral center is changing from R to S, and also S changing to R. If you look C and D, you can also realize that our chiral center changes from R to S, and it is also changing from R to S. When a chiral carbon changes from one configuration to another, it's become enantiomers. So we can say that C and D are enantiomers. Enantiomers. And also A and B are also enantiomers. Remember, we have said for enantiomers, the two chiral carbons has to change. For example, take A, it changes from R to S, and in the same carbon number 2, it changes from S to R. So those are enantiomers. When those are enantiomers, then it means A and C then, so we're going to have A and C. We can have B and D, and we can have A and D, and then we can also have C and B, All of them are called diastereomers. Why do we say diastereomers? So I want you guys to look carefully. Now, I have redrawn our molecules that we have. Now, we are saying that why will we say C and D are enantiomers? We have said if you look C and D, they are enantiomers because now carbon number 4 is changing, the chiral carbon is changing from R to S, and in carbon number 2 in the same C, it changes from R to S. When two chiral carbons changes completely their configuration, then it's become enantiomers. Just like in A and B, if you look A and B, carbon number 4 changes from R in A to S in B, and carbon number 2 changes from S in A to R in B. So that's our enantiomers. And then we are saying that diastereomers are molecules in which if you have two chiral carbons in two different molecules, only one is going to change while the other does not change. For example, we are saying that A and C are diastereomers. If you look carbon number 4 in A, it is R, and in C, it is also R. But if you look carbon number 2 in A, it is S, while in carbon number 2 in C, it is R. So it is only carbon number 2 in both A and B which has changed, in A and C which has changed, but carbon number 4 has maintained its configuration, and therefore A and C are diastereomers. Now, if you look B and D, we are also saying that B and D are diastereomers because if you look in carbon number 4, we have S configuration in B, and in D, we also have S in carbon number 4. So carbon number 4 configuration or stereochemistry has not changed. But if you look in carbon number 2, it has changed in B from R to carbon number 2, which is S in D. So that one, it has changed. So because only one chiral carbon has changed while the other has not changed, then it does not qualify to be enantiomer, but it is diastereomers. So also you can look C and B. You can look C and B. If you look C and B, carbon number 4 is S in B and it is R in C. So meaning that that one has changed. But carbon number 2 is R in C and it is R in B. So meaning that it has not changed. Look at also A and D. Let's look carbon number 4. So carbon number 4 is R in A and it is S in D. So there's a change of configuration. While carbon number 2 is S in A and it is S in D. So that one has not changed. So making those ones are diastereomers. So that's sometimes how you can identify enantiomers and diastereomers, and also how you can give them RS configuration. Thank you so much for watching. Hey, remember to subscribe and turn on the notification bell so that each and every time we make new uploads, you get the first person to be notified.
All right, so that is that. And I think with these two, you should be okay to be able to assign R and S configurations when you are giving any molecule with a chiral center. But then what I want to add here is that it is not always the case that a molecule will have only one chiral center. If a molecule has one chiral center, it is expected that you will be able to tell the configuration around that chiral center, whether it is R configuration or S. If the compound has 3 chiral centers, you should be able to indicate at each of the chiral center the configuration. And that's how come we can have RR, RS, SS, depending on the number of chiral centers. But then again, take note that if we are talking about carbon compounds, then always, if the compound is, let's say, an alcohol, then we should be able to number the longest continuous carbon chain such that we will be able to know the carbon number where the configurations are. Because where you have 2 or more chiral centers, okay, and you are calling them R, the question is which R is for which carbon. But if you have numbered the carbon, then you know that, oh, if carbon 2 is R, then that one becomes what? 2R. If carbon 4 is S, then that one becomes what? 4S. So the number of the carbon is then attached to the configuration of the chiral center. And then again, another point I also want to raise here is that for a compound that has maybe 2 or more chiral centers, like we saw the last time, you need to be able to calculate how many forms it will exist. If it will exist in 4 forms, you should be able to let us know all the 4 stereoisomers. And if there are 4 stereoisomers, you should be able to tell which ones are showing enantiomers or are enantiomeric pairs, and which ones are diastereoisomers. And of course, the enantiomers always have mirror image relationship. So if this one is R, the other one will be what? S. If this one is RR, the other one will be what? SS. If this one is what? RS, the other one will be what? SR. The enantiomers always are like opposites, that mirror image relationship, and then they are not superimposable. And so that is that. Then in getting the diastereoisomers, that is the rest of the stereoisomers. Mostly, you know, when you have 2 enantiomers, then they can cross to give you the diastereoisomers, molecules. So that is that. So we'll just end here on the R and S configuration. Then I'm going to introduce you to other stereo isomers or stereochemistry, identification of molecules. So we are saying that apart from let's say a molecule having a chiral center and then not having a plane of symmetry means that the molecule is optically active. And for that matter, it will exist in different forms, and how to determine the number of forms and then how to assign the configurations, we've looked at them. But then beyond that, we also have cyclic compounds, okay? We have cyclic compounds. All compounds are not straight chains. The examples we've given so far are all open chain organic compounds. What about when you have cyclic systems? Okay, how do we assign, how do we describe the stereochemistry? And that's what I'm going to take you through with some examples. So the stereochemistry of ring systems, you are looking at ring compounds. And please, can you see my screen? All right. So at least we should be able to know what the cyclic compound is. And then substitutions on cyclic compounds. The substitution can either be mono substituted, meaning we have one substituent. It could be di-substituted, meaning we have two substituents. And then also we can have difference between the cis and trans. And then determine whether these cyclic compounds are optically active or inactive. So let's take the cyclopropanes. Cyclopropane have 3 carbons in a ring form. And so you can see over here a ring of 3-member ring with a substituent lettered A. So this is a mono substitution because there's only one substituent on it. And this group can be any substituent at all. It can be an OH, it can be an NH2, it can be a methyl group, you know, any. Now, the stereochemistry of mono-substituted cyclopropanes is as simple as that. You can have a plane of symmetry between them. Whether there's a chiral center or not, that is not our issue. You could see that if you have this, you can cut through where the substituent group is, okay, and get 2 equal fragments. Because you can cut it into 2 equal fragments through the substituent, it does tells you that there is a plane of symmetry. Now, remember, I have told you that 2 criteria always give rise to optical isomerism. 2 criteria always give rise to optical isomerism. The first one is that you are looking for a chiral center. And we know how a chiral center or a chiral carbon or a stereogenic center is. The second thing is that you want to be sure that the molecule under question does not have a line of symmetry or a plane of symmetry. And here, when we talk about symmetrical, asymmetric, we use objects to explain. And then that was our first lecture, how to identify asymmetric and symmetrical objects. And then we translated that one into molecules. So when we say a molecule is symmetrical, I mean, you can dissect it, you can cut it, you can divide it into 2 equal halves. And whenever a molecule has a plane of symmetry, it does destroy its chirality. it does not make it optically active again. And any molecule that is optically inactive will always exist as one compound. It is when the compound exists as what? Optically active, then it can exist in different forms, of which you can then calculate the number of what? Different forms. So if you are asked to describe the stereochemistry of a monosubstituted cyclopropane, then you should know straight away that such molecules will possess a plane of symmetry, and hence they are optically inactive. And because they are optically inactive, then it means they will exist in only one form. So let me give you an example. You have your pens close to you. You have your pens close to you.
Yes,
all right.
yes.
So all of you should take this compound, methyl cyclopropane. Methyl cyclopropane. Draw the structure. Now, if you are able to draw the structure, now the question is, describe the stereochemistry. Describe the stereochemistry. Yes, anyone who wants to try? Yes, anyone?
Look,
Yes.
there is a plane of symmetry. There is a plane of symmetry, and also there is no chiral center, and um, because there is no chiral center, the compound is optically inactive, and hence it exists in only one form.
All right, that is good. That's a good attempt. Anyone? So he is saying that for methyl cyclopropane, first, he's unable to identify a chiral center, which is one of the conditions for optical activity. Secondly, the molecule itself has a plane of symmetry, which is the second condition for optical activity. So if the methyl cyclopropane do not meet these two conditions, then it can be said that the molecule is what? Optically inactive. It is inactive, optically inactive. And anytime you make this statement that a molecule is optically inactive, then the conclusion is that the molecule will exist in one form. So when we say describe the stereochemistry, these are the key points. First of all, you need to use the two conditions to establish whether the molecule is active or inactive. So you want to say there's no chiral center, there's a plane of symmetry. As soon as you're able to establish these two conditions in the molecule, then it tells you that, oh, then this molecule is optically inactive. And that is a statement you need to make. And when you make that statement too, you need to draw a conclusion. If a molecule is optically inactive, then it means that the molecule will exist in one form. Exists in one form. Conversely, if the molecule probably had a chiral center, and then again, there's no plane of symmetry, you also make that statement that, oh, the molecule has no plane of symmetry or a line of symmetry. And here, that statement means that you cannot cut the molecule into two equal halves. and then there's a chiral center. So based on that, you can then say that, oh, the molecule is optically active. And anytime you also make this conclusion or this statement that a molecule is optically active, any optically active molecule definitely will exist in different forms. So you should be able to tell us how many forms. And that is where you probably will want to use the number of chiral centers there to do your calculations. Okay. And again, also apply the cis and trans. We'll get there soon. Then you can then say that, oh, so for that reason, the molecule will exist in 2 forms or 4 forms. Okay. And then you make that statement. So that is a good attempt. And so let's look at other types of what? Cyclocompounds. So we can also have the 1,1-disubstituted cyclopropanes, and they also behave similarly to the monosubstituted ones, these ones, where you have 2 substituents A and B, but then both are on the same carbon, 1,1 di. And those ones too, you could see that you can have a plane of symmetry. You can cut it into 2 equal halves. And so you say they possess a plane of symmetry. And if they possess a plane of symmetry, then automatically they are optically inactive. And if they are optically inactive, then it means that they also exist in one form. So the 1,1-disubstituted and then the monosubstituted behave similarly in terms of their stereochemistry description. But when you move to the 1,2-disubstituted, where the 2 substituents are on different carbons, of which is a cyclopropane, okay? Of course, for cyclo compounds, there are many. We have 3-membered ring, 4-membered ring, 5-membered ring, 6-membered ring, 8-membered ring, and then the substitution can vary. We can have the mono-substituted, you can have the 1,1-disubstituted, you can have 1,2-disubstituted, you can have 1,3-disubstituted, you can have 1,4-disubstituted, and so on and so forth. So the different, substitution and then the different ring size brings about different stereochemistry. And you should be able to, I will share this information with you. This one, I had to prepare this slide from the model, the stereochemistry model, of which I don't know whether you have it. Do you have it?
No, sir.
Okay.
No, sir.
Because, I have given you a summary lecture slides, which is good. But that one did not include the stereochemistry of the ring compounds or the ring systems. And this one is what I extracted from the model. So maybe I can also share this one with you. If you like, you can just check my last year and last 2 years questions. And there's a question that I normally ask over here. So when we talk about the 1,2-disubstituted, as you can see, I and the II, you could see that when the substituents are on different carbons, then we can arrange them in the cis form or the trans form. So for 1,2-disubstituted cyclocompounds, always know that you have to deal with the cis isomer, discuss their stereochemistry, then you look at the trans isomer and also discuss their stereochemistry. Then you combine the two. So in the case of the cis isomer, I and the II, we are going to look at their stereochemistry. Then we'll look at the trans. You see that the trans, the A and the B, the 2 substituents, they are in opposite direction. Okay, the same thing here. They are in opposite direction. So we can have 2 forms of the cis isomer and then 2 forms of what? The trans isomer. But of course, the I and the II are showing a mirror image relationship. Okay, if you draw a mirror line between them, then you can see a mirror image relationship between I and II. Then again, if you draw the same mirror line between III and IV, they are also showing what? A mirror image relationship, meaning I and II could be enantiomers. III and IV could also be what? Enantiomers. What that means is that I and III could be distereoisomers, and then II and IV could also be what? Distereoisomers. So we are saying that for 1,2-disubstituted cyclopropane, because of ring the rigid ring structure, okay? You know, cis and trans isomerism always takes place whenever there's that kind of rigidity. You know, in the carbon-carbon double bond where we have rigid rotation around the double bond, then there's what? Geometric isomerism. So here too, the rigid ring structure brings about cis and trans isomers. And so you need to deal with the two. Now the cis isomer, which we are considering as the I and II, they lack elements of symmetry. Okay? They lack what? Element of symmetry. Meaning there's no plane of symmetry and there's no line of symmetry. Okay? For that reason, they are not superimposable and hence they are optically active. If they are optically active, then it means that two different forms are possible. So the cis isomer produces what? Two possible compounds. Now, if you look at the trans isomer, over there, the IV is not superimposable on the III. But then the trans form also exists in two forms. Okay? The trans form also exists in two forms. And so let's go back. I want to go back to those ring structures. So what that we are saying is that if you take I and II, though they are mirror images, they are not superimposable. They are not superimposable. And because A is not the same as B, you cannot say, oh, I can divide the molecule into two equal halves. So there's a line of symmetry or there's a plane of symmetry. A is not the same as B. So you cannot divide it into two equal halves. So there's no plane of symmetry. There's no line of symmetry. For that reason, these two compounds, I and II, exist as two different compounds because the cis isomer is behaving as an optically active compound. And so if it's an optically active compound, then it will exist in two forms. And the two forms are the I and II. The same thing applies to the III and then the IV. You cannot cut it into two equal halves. There's no plane of symmetry. There's no line of symmetry. Okay, as you can see. So it means that though the III is a mirror image of IV, they are not superimposable. So they are two distinct compounds. So that one too exists in two forms. So in actual sense, if A is not equal to B, then the 1,2 disubstituted compound you can see here, which will have the cis isomer existing in two forms, and then the trans isomer also exists in two forms, together will exist in what? 4 different forms. 2 from the cis and then 2 from the trans. But if you go further to define A and B, and then A and B are the same, if A and B are the same, then there will be an element of symmetry in the cis isomers. So because this A, if it's the same as this B, then it means that a plane of symmetry exists. And if a plane of symmetry exists, that destroys the optical activity of the molecule. And any molecule that is optically not active is considered as what? Optically inactive. And if it is optically inactive, then that molecule can never exist as what? 2. Meaning the I and the II will be the same compound if A is equal to B. So it means that the two compounds you see here is 1 because of what? The plane of symmetry that exists. Of course, if A is the same as B, because this one is the transform, you see, and they are pointing in opposite direction, it will be difficult to have a plane of symmetry in between them. So the trans will still exist as what? Optically active and 2 different forms, but then the cis will exist as what? Only 1 form. So it means that 1 here and 2 here, then it means that the whole molecule will exist in 3 forms. That is if only A is equal to what? B. Again, if you have your pens and pencils close to you, I will want to give you some compounds and then you describe their stereochemistry. And the example I'm going to give you are the ones that I just described, the 1,2-di substituted cyclopropane. Are you ready to write?
Yes, doc.
All right. So write the question. Describe the stereochemistry
Doc,
of
please again.
describe the stereochemistry of 1,2-diethyl cyclopropane describe the stereochemistry of 1,2-diethyl cyclopropane. 2, 1-ethyl 2-methyl cyclopropane. So I've given you two different compounds. 1,2-diethyl cyclopropane and then 1-ethyl 2-methyl cyclopropane. So describe the stereochemistry of these two. First of all, since they are following this trend, 1,2-disubstituted cyclo compounds, you need to look out for possible cis isomers and then trans isomers. Then you discuss the cis isomer from the trans isomer. And in both cases, consider the two, whether there's an element of symmetry, which will destroy the stereochemistry or not, and then come out with the possible forms. So I'm giving you some 5 minutes or 10 minutes to try your hands on this, and then we'll get back to discuss it before we move on. Yes, please, are you done? Or you need some more time? Are you done? Hello.
Hello, sir.
Hello, sir.
I want to know whether you are done or you are still trying your hands on it.
I need to, but we have reached certain point here. So unless you finish it fast.
Okay, so I will come on board, but then let me know what you'll be able to put down in terms of you trying to describe the stereochemistry of these two compounds. Just let me know how you went about it, and then let me also know what to add up. Yes, so anyone, yes, Esiama.
So the first one, which is 1,2 dimethyl cyclopropane. There's a line of symmetry. Therefore, it makes it inactive. Also, there's no carbon, making it to be having only one form.
That is the 1,2 diethyl cyclopropane.
Yes, please.
Okay, move to the second one.
The second one, which is 1 2-methyl cyclopropane. There is no line of symmetry, therefore making it active. There is one carbon, therefore giving it two forms. This is what I have for the two.
Yes, any other person?
Yeah, my own too.
Yes, go ahead.
For the 1,2 diethyl cyclopropane, I found out that it has two forms. It has the cis and the trans.
Okay.
And that the cis part, I think there is a plane of symmetry in the cis. And since there is a plane of symmetry, I considered it to be inactive. And also there were two chiras. No, there were no. There were two chiras in this. The cis, and then the trans part of it was there was no symmetry in the trans. It wasn't superimposable, and it was active. But the second one, I didn't finish.
Okay, can I get a third person, and then I'll come on board and give you how I would want you to go about in your presentation in an exams, because definitely there will be a question of this similar sort in an exams. So a third person, then I'll come on board. Yes, anyone? Or I should go ahead. Should I go ahead?
Nice.
All right. Please, you see, before I go ahead, I gave you 1, 2 diassociated, cyclopropane. But you can see on the screen that currently what cyclopropane is a 3-membered ring, but then what you see here is a 4-membered ring. So the same idea that I'm going to give you is what you apply, even if it is 1, 2 cyclobutane or cyclopentane or cyclohexane. Okay, so the understanding and then the principle, get it once and then you apply to other systems. First, most of you were saying active, inactive. Please be very, very specific here. We are doing stereochemistry, so your choice of words is key. It is either optically active or optically inactive. Don't just say it is active. Don't just say it is inactive. Make sure you add optically active or optically inactive. So those of you who were presenting your answers, take notice of that. Then you see, I gave you 2 conditions. Chiral center, no plane of symmetry or line of symmetry. Then you say that the molecule is optically active. The one thing that I want you to also take it clear here is that a molecule can have a chiral center. All right. But then if the chiral center that is there, whether it's 1 or 2, if the second condition, which is plane of symmetry, it has a plane of symmetry, that plane of symmetry, as it were, overrides the presence of a chiral center. In fact, the plane of symmetry destroys chirality. So you might have even initially identified a chiral center or a chiral carbon, but it is immaterial at this point if there's a plane of symmetry, because that plane of symmetry will then destroy the chirality. So the effect of the chiral center doesn't even matter as to the number of forms. I hope you are getting this point too clear. So in this case, if I pick the 1,2-diethyl cyclopropane, we have already said that when we have a 1,2-disubstitution cyclopropane, then because of the rigidity of the ring, okay, how rigid the ring is, it brings about the cis and trans forms. So the 1,2, you can have the cis and then the trans form. And you see the previous, let me go back. You see that I drew the
Hello,
2.
sir.
Yes.
Okay, sir, please, I'm having a problem on the structure, so please, if you can draw it for me, the cis and the trans ones.
That's what is on the screen. You see the cis isomers,
Oh.
you see that A and B are all pointing upwards, the same side.
Oh.
Have you forgotten cis isomer in alkenes and then alkynes?
Sure.
When we're doing
Sure, sir.
okay, so for the cis structure, we say 1,2-diethyl. So there are 2 ethyl groups. So it means that the ethyl group. So now you bring one bond here, okay, so they become ethyl. When you come here you bring another one here, okay. But then the point is that the 2 ethyl groups are all pointing to the same side, and it makes, and because now the 2 substituents are the same. You see over here, the A is not the same as B, so there's no plane of symmetry. But if A here and then over here too, you have A, okay, because you have the same substituent A and A here, then there will be a plane of symmetry. So the diethyl I gave you, it means that A is now equal to B. So the 2 ethyl groups pointing to the same side brings about a plane of symmetry. And so far as there's a plane of symmetry, forget about whether there's a chiral carbon or there's no chiral carbon. The plane of symmetry destroys the chirality of the molecule. There's a plane of symmetry, and any molecule that has a plane of symmetry it is automatically optically inactive. So you make that statement. So your first statement is that 1,2-diethyl cyclopropane will exist in the cis and then the trans form. That is the first statement. Then you draw the cis isomers where the two ethyl groups are pointing to the same side. And because they are pointing to the same side, that makes them the cis. You then make a statement that there is a plane of symmetry in the cis isomer. And that plane of symmetry destroys the optical activity of the molecule. So the molecule is said to be what? Optically inactive. You have to make that statement to earn a point, to earn a mark. And when you have made that point that the cis form of 1,2-diethyl cyclopropane is optically inactive, then you need to conclude. What does that mean? It then means that any optically inactive compound will exist in one form. And all this thing that you are saying is for the cis isomer. So the cis isomer will exist in one form. Yes. Yes.
Please, the 1,2-di substituted. If the A is not equal to B, for the cis, will you still get a plane of symmetry?
No, you will not. And that's why I told you that for the cis and then the trans isomer, as it is on the screen, if A is not, of course, A can never be B. The letter A is not the same as B. So here, the implication is that they are two different what? Substituents. And if they are two different substituents, there's no way you can cut it into two equal halves. So there's no line of symmetry or plane of symmetry. And that makes it what? Active, optically active. And because it is optically active, it will exist in two forms. That is the I and then the II, its mirror image. But if A, as I gave you in the assignment I just gave you to try your hands on, that eta means that the two groups are all eta. It means that they are the same, meaning A and B are the same. Where A is the same as B, in this case, that 1,2-diethyl cyclopropane, then you can cut the molecule into two equal halves. So there's a plane of symmetry, and that plane of symmetry will make the cis form optically inactive. And if the cis form is optically inactive, it will exist in only one form. But that is not the only one, because that is the cis one. Then you go to the trans. Now, when you come to the trans, you realize that even though it is 1,2-diethyl, okay, but the ethyl, one is pointing up and one will be pointing down to show that this is trans. And because one is pointing up and one is pointing down, if you cut it into two equal halves, it is not possible. What will be on the left side will be different from what is on the right side. So it means that for the trans isomer, there is no plane of symmetry. And if there's no plane of symmetry in the trans isomer, then you want to say that the trans isomer of 1,2-diethyl cyclopropane is optically active. And if it is optically active, then it will exist in what? Two forms. That is this III and then the IV is mirror image. And you draw it. So now the cis is one form, the trans is two forms. So together, how many forms are you getting? 3. So the molecule 1,2-diethyl cyclopropane will exist in 3 forms. 1 from the cis isomer, 2 from the trans isomer. Please, is it clear? Is it clear?
Yes, sir.
Good. Now the second one I gave. So I said 1 ethyl, 2 methyl. So over here, the two substituents, even though it is 1, 2, I've made one of them ethyl group. Okay. Then the other one remains what? Methyl. So far as the two substituents are different, over there too, there will be cis and trans. The cis form will not have any plane of symmetry because here the two substituents I've given you are different. 1 ethyl and then 1 2 methyl. So there's no way you can cut it into 2 equal halves. So there's no plane of symmetry, and then the cis form will be optically active. And if it's optically active, it will exist in 2 forms, as you can see, the I and the II. But you draw it where one of these will be a methyl, that's a line like this, then the other one will be an ethyl. Then you draw its mirror image. Then when you come to the trans, that one, because even the transform already is optically active, and then the subsequent two are different, then that one will exist in two forms, as you can see, and then you draw it. So the 1 meter, 2 meter will exist in cis form. The cis form will have two forms because there's no plane of symmetry and it is optically active and it will exist in two forms. The transform is also having no plane of symmetry, and so it is going to be optically active and it's also going to exist in two forms. So 2 plus 2 making what? 4 forms. So the 1 meter, 2 meter cyclopropane will exist in what? 4 forms. So that is that. So it's the same understanding and then the same principle. If you look at the other, you see that now it's no more cyclopropane, but then cyclobutane, 4-membered ring. But then we have mono substituted, and then we have the 1-1. The two of them are all going to have a plane of symmetry. So they will be what? Optically inactive, and they will exist as what? One form. But when you come to the 1-2, over here too, you have the cis and then the trans. Now the cis form, okay, if B and A are not the same, then it is going to be optically active, and the cis will exist in two forms. The trans will also exist in two forms. But if B and A are the same, then there will be a plane of symmetry, and then the cis will exist in one form, but then the trans will exist in two forms, making it what? 3. But this one is even a 4-membered ring, cyclobutane. So the same, so as I've indicated here. So hence exists in 4, okay, forms. If A is equal to B, look at the statement here. If A is equal to B, then the cis form possesses a plane of symmetry, therefore becomes inactive. And if it's inactive, optically inactive, then it will exist in one form. But then the trans form still lacks a plane of symmetry, and that transform will therefore exist in two forms. And so we move to 1-3 that substituted over there to have cis and trans. We move to 1-4 that substitutions. So I will share this information with you, okay, so that you have a fair idea on whichever substitution that you are giving, how you should go about describing the stereochemistry of these cyclic compounds. Any question? We will end the class after the question.
Question.
Yes.
When you were describing the stereochemistry, you didn't list or you didn't make mention of whether the cis one has maybe one chiral center or two or something.
Kofi, I made a statement earlier on that when you are describing it, don't just say active or inactive. I said that make sure you add the word optically active or optically inactive. And no, hold on. Pay attention. I know your challenge. That's why I'm taking my time. That before I even went through the discussion of how the answer should be, I made 2 statements. The first one was that when you guys were presenting your answers, you were saying active, inactive. And then I drew your attention that in an exams, if you do that, I won't give you the mark. Make sure you say optically active and that it will exist in these forms, or optically inactive, it will exist in one form. That was the first correction I made. The second statement I made, which you still have to listen and get it right, is that the 2 conditions that I gave you, okay, that give rise to what? Optical activity. 1, you are looking for a chiral center. 2, that there's no plane of symmetry. But I added that there are situations whereby the first condition will be met. That is, you might even see a chiral center. Okay, but though there's a chiral center, maybe 1 or 2, but because the molecule has a plane of symmetry, that second condition, which is the plane of symmetry that the molecule is having, it is coming in to destroy or do away with the first reading. So it doesn't even matter again whether there's a chiral carbon or there's no chiral carbon. So far there's a plane of symmetry, that one overrides the first condition. And I made this statement right here. Are you getting me?
Yes, please.
So even if it is not a cyclic compound, let's assume that I give you tartaric acid. Tartaric acid has 2 acid groups. It's a 4-carbon chain diacid, 2 carboxylic acid groups at the end, and then there are 2 chiral centers. But the tartaric acid, okay, has two forms, the trio and then the erythro. Now the trio forms has a plane of symmetry. And so you can then cut tartaric acid into two equal halves. Even though there are two chiral centers, because you can cut it into two equal halves, that plane of symmetry, okay, takes precedence over the two chiral centers that you have identified. And it makes the molecule what? Optically inactive. So what I'm trying to say is that in a situation where the second condition, which is the plane of symmetry, is seen, forget about the number of chiral carbons or chiral centers there. It overrides that first condition and makes the molecule what? Optically inactive.
Oh, okay. Thank you.
Good.
Thank you.
Good. You're welcome. Yes, Asiama.
Look, mine is just I want a confirmation. So to make the conclusion, you need to draw the cis and trans for the molecule given before you can make the conclusion, but not only on one.
Yes.
Okay.
So you see, that's what I said. So I'm giving you this ones as a guide, so that in an exams you do the right thing. If you look at most of my past questions, sometimes I will give you the structures myself. I will give the name and then the structures. So that one you might not have much of a problem. As soon as you yourself you see the structures, you will be looking at a chiral center and the plane of symmetry. And like I was telling Aaron, if you have even seen one chiral center, but then you see a plane of symmetry in the molecule, that one overrides the presence of a chiral center and the molecule becomes optically inactive. And if it's optically inactive, it exists in only one form, irrespective of whether it has one chiral or two chiral centers. Okay. So you need to draw. If I give you only just the name, you need to draw the structures. And if you are unable to draw the name of the structures, it can even affect your answers. But in most of my questions, I think I had even attached the structures to the questions, for easy identification.
Okay, sir. Thank you.
I will share this one. If you have the course model on stereochemistry, it is all in there. But if not, I have developed this slides from it. This is Unit 3, Section 1, up to Section 6. I can share that one with you also to serve as an additional material in your revision. But then the lecture has been recorded. So when you go back and then you sit down, I'm sure you also will appreciate how to describe the stereochemistry of what cyclic compounds. Okay. So please, we will end here. Go and then ponder over what we've done. And then I think the course rep should do something for the class. These slides, I said I will share. Try and pull me. I'm a bit busy, but try and pull me and let me share with you. I talk about tutorial questions and then review questions. The last meeting, and then still I am aware that I have not shared that information with you. So I don't know what you guys are trying your hands on to appreciate the topics that we have done so far. You need those informations, please, before your quizzes and then. All right.
The description. Can we write it in a point form, or if you write it in essay if you are the scriber?
It can be point by point. The key point is that if it can exist in the cis and trans, you make that statement. Then you deal with the cis alone by drawing the cis structure. Then you make a statement of whether there is a plane of symmetry or not. And that statement, if you say that there's a plane of symmetry, it means what? It means that the molecule is what? Optically inactive. And if a molecule, we made that statement, molecule is optically inactive, then what should follow is that the molecule exists in one form. Okay. If you also make the point that the molecule is what? Optically, there's no plane of symmetry. If there's no plane of symmetry, then it means that the molecule is what? Optically active. And if you make that statement that the molecule is optically active, what does it imply? It also implies that the molecule exists in what? Two different forms. That is the compound and its mirror image. Then you draw the two forms. I hope that's clear.
Okay, thank you.
Okay. I'm getting this thing here. Okay.
Doc. Hello, Doc.
Yes.
You promised giving us the slides that you developed from the
Yeah,
model.
you tell me to chat him.
Oh, okay.
Yeah, this ones. There are a number of them I have. There are a number of them I have, which I have to share with you because some of them, the way I have done it, it makes it simple to follow the slides than maybe going for the whole model.
Okay, sir. So our rep, Asiama will follow you up and help us to get it. For today, the never mind kaka fine. But I believe that
don't worry, you'll be fine. I must be very frank with you that stereochemistry is one of the areas of chemistry which even is difficult to even get people to come and lecture because the course itself it's not easy. You need to have that kind of mastery, and so it's no course a course that it's one of the troublesome chemistry courses, but you overcome it. Okay, you overcome it. That's why I'm saying that you need all that I'm talking about, all that you'll be watching from the recorded video, or that you yourself will be reading from my slides. There's a need for you to also look out for my tutorial and review questions, and then see how questions can be. Yeah.
So, Asiama, are you here? Make sure you deliver the goods for us. So, I said, Okunuma Eden. Okunuma Eden, but yeah, bro. Paul. Paul, Okunuma Eden, I'm already.
I don't the day you get your A's. You get your A's and B pluses.
Network is week in, I'm going to use the laptop online. Phone machine in tune. Yeah, one penny. Also, machine. Paul, that's small.
Hey, I'll say about
Kaka. The doc and I, yes, Senator, on good Yamamu and Kaka.
Yeah, no, I don't wear lifeline. Direct question, direct answer.
Okay, sir. But I'm okay,